So today's lesson, quoting Sesame Street here, today's lesson is brought to you by the letter E. And really, I probably should say the number E, because for us in math and in Algebra 2, but really in math in general, we study the letter E as actually the number E, right? And that's different. That's something that's a little bit tough to think about. When we started looking at I, it was tough for us to think about how does this letter really represent a number. Well, I represents the square root of -1, and so it introduces a whole new set of numbers, the complex numbers. E is not quite as exciting. E is simply an irrational number, so it's just a regular real number, just so happens that it's irrational, right? It's approximately 2.7182818, and so on and so on and so on. The thing to remember is it's irrational. There's no repeating parts. Even though we see this like this 1/8 and this 1/8 and kind of that 8/1/8, and you're kind of thinking, oh, maybe it's going to repeat this 8. No, it never repeats. It's like pi, right? Or even the square root of 2. Irrational numbers that never repeat. E is just an example like that. Okay, E is found with the equation, or found with this equation, right? The function evaluated at n equals 1 plus 1 over n raised to the nth power. Kind of a weird equation, but if we graph it, we can kind of see, okay, when n is 0, which n probably can't ever equal 0, but as n gets really, really close to 0, really, really small, okay, we just get a small number here. Okay. But as n increases, and so on, as n gets really, really big, it just keeps approaching and approaching this number. And the reason it does that is because of this fraction here. As n gets big in the denominator, this fraction gets smaller and smaller and smaller. So even though n is getting huge here, it's also going way down here. They kind of have an inverse relationship, right? Not particularly because this is division and this is exponents, and the opposite of division is multiplication, and the opposite of exponents is logarithms. So they're not actually inverses, but n forces this fraction, as n gets big, this fraction gets small, but as n gets big here, the exponent gets big. So the stuff inside the parentheses is essentially approaching 1, really, really small fraction, while the exponent is getting really big. Okay? It's a weird equation, but it's so cool. Okay? Well, I think it is. You probably don't. You think I'm crazy. I know that. Okay? But when we see it in the graph, we can really see, okay, it's going to be approaching an asymptote, and that asymptote is y equals e. That number e, that irrational number e, is our asymptote for this equation. Okay? So that's where E comes from. And you'll study that more in calculus when you get into limits and all sorts of even more exciting math, but for now, you just need to understand that E is a number, and it's approximately 2.718. Right? Now, with E being a number, it introduces the natural log. And the natural log is a log with a base of E. Right? We've dealt with logs. We've dealt with log base 10, which is the common log, which is the log we see when we see log on our calculator. And we've dealt with log of any other base because sometimes we have bases we can just work with naturally. Or easily, I should say. I shouldn't say naturally. Easily. Well, the natural log, abbreviated LN, and that's a button on your calculator, you could look for it right now, means that we're looking at the log with base E. Log base E is our natural log. Right? And it's still the inverse of e to the x. E to the x has an inverse of the natural log of x. Okay? And you can see that relationship here, right? Here's the function e to the x, going up, reflected across the line y equals x, right? Switch the x and the y. And then right there is the graph of the natural log of x. Okay? We work with natural log, and this third line is really important. Natural log is treated the same. We can use the same properties of logarithms. We can use our same steps for solving with natural log. It's just that the base is now something different. The base is locked in as E. That's 2.7, blah, 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 whatever. The base is E, right? Natural log and E go together the way 10 and the common log do. Okay? So really, we need to be able to work with E, and we need to be able to work with natural log. Now, there's some great applications of E in the real world. The first is continuously compounded interest. I'm going to talk to you about, think about credit cards, right? you'll hear things like, I got an APR, and if you haven't heard this, ask your parents about their credit card, right? You can get an annual percentage rate of how they charge interest for you, and it's continuously compounded, which means like after you earn interest on your bill for 1 month, then you earn interest on that new amount for the second month, and then that new amount, and so on. Okay? This formula is how they calculate that, which is so cool. Like, this is actually happening. Like, my credit card bill right now, this is happening to it, essentially, right? A is the total amount. The total amount after interest. You can think A after we've taken the interest. P is the principal. Not Mr. Darlene, not Mr. Lutz. No, the principal is the initial amount invested. And really, I could easily say the initial amount charged on a credit card. Just the initial amount in general. E is E. Oh, look at how happy it is. Okay, anyway, but E is E. So we'll just treat that as E like we see on our calculator. R is the annual interest rate. Like, okay, so you'll hear things that say, like credit cards, they'll say you have an APR of 0% for 18 months. And then when you start to read the fine print, turns out then after 18 months, which that's not bad to have 0% right away, but then after 18 months it jumps up to like 28% or like that. Okay? It's always important that you really read a credit card application. Okay? So what is the annual interest rate? That goes up here in the R, and then the time is in years. Okay? So, because if it's an annual interest rate, then it makes sense that the time would also be in years. Right? The rate and the time should kind of fit together. 28% per year, time in years. So that it always works together. You don't want a time in months when your rate is in years and vice versa. You want those units essentially to match. I would write this formula down if I were you, and I would for sure record what these letters mean. I mean, it's not enough to know a formula. You probably want to know how to use it. Right? Okay, the second formula I'm going to show you, and this one we're going to take a closer look at it in class, is natural decay. How does carbon, for example, or how does uranium, for example, or how do elements decay? Okay. This formula, N of T equals N naught e to the negative kt. Like, so many letters. It looks like it spells Noeket. That's not actually a thing. It would be cool if it were, but we actually have specific things. So N of T is the amount remaining. How much stuff is remaining after a particular time t? N naught. This 0 here, when we say it N naught, I know people say N naught. I know both are good. I learned N naught. So N naught is the initial amount. When t equals 0, how much do we have? How much carbon is there? How many atoms are there? Whatever. Okay? That's the initial amount. The amount when t equals 0 is N naught. E is E. So happy. K is the decay constant, right? As if K is large, that means our stuff is going to decay really quickly. But if K is smaller, it's going to take longer for T to decay. So really, this is almost like our rate in the previous example, except for now we're talking about how quickly something decays or wears away. Okay? And then T, of course, is time. And time in this case is in years. Okay? It's a kind of a little bit more complicated formula than the one you just looked at, especially because of this decay constant. So that's why we're going to take a closer look at that and make sure we talk about that in class. Now, half-life, right? You've heard that phrase, I hope. I hope you've heard the phrase half-life. If not, you're hearing it right now. Half-life is the time it takes for half of a substance to decay, right? You can read that. I don't know why I just read that to you. But really, half-life is how long until half is left, right? As stuff is decaying. It always takes the same length of time to get to half. So if you have a half-life of 50 years, let's say you start with 100 atoms, I'm just throwing out science words, you have 100 atoms. After 50 years, you'll have 50 atoms. After 50 more years, you'll have 25 atoms. The half-life is constant. It's always the same for a given substance, right? That's the idea of substance. Okay? So even as your substance decreases, the half-life is always the same. So to go from 25 to 12.5, it'll take 50 years. to go from 10,000 to 5,000 will take the same amount of time as to go from 50 to 25. Right? It's a half-life. It's a specific amount of time. And it doesn't matter how much there is. That half-life is constant for every substance we have. Okay? So natural decay is the second sort of application of E, and we're really going to look at that. I mean, you've got logarithms down, so and exponential equations down, and how to solve them, and all sorts of that fun stuff. So we can really play around with this equation, and then of course the equation for continuously compounded interest. So make sure you have both those written down. If you need to, go back. You can mute me if you're sick of listening to me, but go back and write it down so you have it. Please take the time to do that. It's really important. I want you to do well, but you have to put the work in. So write that formula down, write down what the letters mean so you have a reference, and so that you just know. I mean, there's lots of letters. We need to be able to keep track of them. Okay, so please make sure you're writing these things down. E is so cool, you guys. Like, I really hope you learn to love it, just because, like, it does a lot more for us. I mean, we work base 10 a lot. We also work base E a lot, and that's really where we see our applications, right? In science and all sorts of stuff like that. And we'll talk more about this too. Like, I think it's important you guys realize how cool E actually is. So, write some good notes down, go back and think through this, be ready to talk problems and actually do some stuff with it when you come to class. Thanks, guys.